Hi, I'm Dr. Jackie Davis, and I'm the head of the Heliospheric Physics Group at STFC RAL Space. And today I'm going to give you a brief overview of the Lagrange Space Weather Monitoring Mission, and in particular, RAL Space's role in that mission. So, firstly, what is space weather? Well, space weather is defined as the effect of the sun on human technologies and health. And while the beautiful lights of the aurora are a welcome effect of space weather, other potential space weather effects are less desirable. For example, the effects of space weather associated radiation on passengers and crew of aircraft, particularly those aircraft on transpolar routes, disruption to the electricity grid due to large induced currents, and damage to solar panels and electronics of satellites. And although we've been experiencing detrimental effects of space weather for centuries, our awareness and concern over space weather has increased rapidly in recent decades due to our increased reliance on technology. So in the UK, for example, this is particularly evidenced by the inclusion since 2011 of space weather on the National Risk Register of Civil Emergencies. So as you can see, space weather, severe space weather that is considered to have a severity of 3 out of 5 and a likelihood of happening within the next 5 years of 4 out of 5. And so as a significant risk, then space weather needs to have a risk owner. And in this case, it's the UK Met Office. So the UK Met Office hosts the Space Weather Operations Centre, MOSWOC, which is one of only 3 space weather prediction centres in the world that provide 24/7 forecasts of space weather. And it operates closely in collaboration with its US counterpart, which is the Space Weather Prediction Centre in Boulder, Colorado. So what is space weather? Well, a number of phenomena on the sun can cause space weather. But actually, the most severe space weather effects are caused by coronal mass ejections or CMEs. CMEs are large-scale eruptions of mass and energy from the solar corona, the expanding solar atmosphere. And a CME can be associated with up to 1 billion tons of plasma moving at speeds up to 2,000 kilometers per second. And it's also worth noting that the prediction of CME arrivals at Earth that we currently rely on are actually based mainly on aging science instruments, on aging science missions, and this clearly isn't a solution for the long term. So the Solar Terrestrial Relations Observatory, or STEREO mission, is a NASA science mission, and this mission has clearly demonstrated the benefits of viewing particularly Earth-directed coronal mass ejections from a vantage point that's off the Sun-Earth line. Now, this is particularly the case when these observations are combined with others which are made from a location upstream of Earth, i.e. the Lagrange L1 point that you can see there on the diagram. Now, this understanding has led to the development of a strategy for space weather prediction that combines a US-led mission to the L1 point with a mission to the Lagrange L5 point, which is 60 degrees behind the Sun-Earth line. And to this end, ESA are developing the so-called Lagrange Mission to the L5 point under their Space Safety Programme. So the Lagrange Mission is scheduled for launch in 2027, is currently entering its so-called B2 detailed design phase. Now the mission will host a payload that includes a suite of in-situ instruments, and they observe the plasma and magnetic field environment in the vicinity of the spacecraft itself, and a package of imaging instruments. The imaging or remote sensing package, as it's known, is led by us here at RAL Space. Note that the in-situ package is led by MSSL, Mullard Space Science Laboratory, and the aircraft itself is being led by Airbus in Stevenage. So I'm going to give you a little bit of an overview of the instruments that have been studied up to now as part of that remote sensing package. And if you see the slide, it shows the breadth of universities, institutes and industrial companies that have been involved in the design and development of the remote sensing package up to now. So starting at the sun, The first Lagrange remote sensing instrument is the so-called Photospheric Magnetic Field Imager, or PMI instrument, that's led by the Max Planck Institute for Solar System Research in Germany. So the PMI instrument monitors the solar surface, or the photosphere as it's called, in visible light. But not only can it observe the activity, complexity and evolution of sunspots, and these are associated with CME eruption, it can also provide measurements of the magnetic field on the photosphere. And it's worth pointing out that the magnetic field of a CME is one of the most important factors in the severity of its interaction with Earth. So viewed from the L5 vantage point, which I'll remind you is 60 degrees behind the Sun-Earth line, is that it enables the observation of an additional 60 degrees of the solar disk that is yet to rotate to a view where it can be seen from the Earth. The PMI instrument is based on the PHI instrument, which is currently operating on ESA's Solar Orbiter mission, which was launched earlier this year. So the second remote sensing instrument is the so-called LUCY instrument, which is led by CSL and ROB in Belgium. So LUCY monitors the lower solar atmosphere, but in EUV, not in visible light, as the PMI instrument does. Now, observing the sun in EUV enables you to see a whole host of features that are simply not visible when viewing in white light, such as prominences, which are effectively proto-CMEs, active regions and flares. Again, the L5 vantage point for an imager, an EUV imager such as this, provides you with an additional 60 degrees of the solar disk before it's rotated into the view of Earth. Now, this can potentially give you an additional 4 days warning time of Earth-directed eruptions. The LUCY design is actually based on the SWAP instrument, which is currently flying on ESA's Probe 2 mission. So the third instrument of the remote sensing package is the visible light coronagraph. Now, a coronagraph acts as an artificial eclipse, obscuring the sun and allowing you to image CMEs directly as they propagate through the solar corona. I don't know if you can see it, but a small white circle in the center of the image that's shown here actually shows the location and size of the solar disk. I mean, coronagraphs are exceedingly important in terms of space weather prediction. They provide the basis of CME characterization for most operational CME arrival forecasts. And indeed, the same CME, if it's viewed from multiple vantage points, here in particular L5 and L1, will allow for a much more accurate prediction of whether a CME will actually impact Earth and what speed it will be at when it does. Although the Lagrange coronagraph is based on the SCOPE design that's currently being studied by RAL Space, it's likely that the coronagraph that will fly on the Lagrange mission will actually be the same US instrument as will fly on the US mission to the L1 point. So the final instrument being studied as part of the current remote sensing package is the RAL Space-led Heliospheric Imager instrument. Now, this is actually based on the Heliospheric Imager that's currently flying on the stereo mission. The Heliospheric Imager on stereo, not that I'm biased, I would suggest is the flagship instrument on the stereo mission. It's worth pointing out that unlike a coronagraph, which observes actually relatively close to the sun, the heliospheric imager can observe coronal mass ejections all the way from the outer corona to Earth-like distances and actually beyond. So while heliospheric imaging then provides a less warning time of CME impact at Earth than a coronagraph can provide you with, it can actually be used as a ground truth to provide mid-course corrections to predictions that are based on those observations just close to the sun. So combined, the remote sensing instruments on the Lagrange L5 mission can actually observe CME precursors and CME propagation all the way from the surface of the sun, the photosphere, to their potential impact to Earth. And the mission itself will form a key part of what is a worldwide strategy for improving the prediction of space weather at Earth. Thank you.